So Copernicus gave the heliocentric model in which he proposed that planets moved in circles around fixed central sun. But church authorities, as the religion was based on geocentric model, where Earth was supposed to be at the center, so that is why church discredited this model. And even Galileo had to face the prosecution and sent to jail for believing the heliocentric model. Okay, so at the same time there was another nobleman, Tycho Brahe from Denmark, and he also spent his entire lifetime recording the observations of the planets with the naked eye. His compiled data was analyzed later by Johannes Kepler, and Kepler could extract from the data three elegant laws that now go by the name of Kepler laws. And these laws were known to the Newton, and which enabled him to give the universal law of gravitation. So Newton proposed the universal law of gravitation based on Kepler laws. Okay, means based on Kepler laws and his own observations. Okay, so now what are these three Kepler laws? First, law of orbit. So here you can see that Copernicus was assuming that planets moved in circles. So that's the change here. So this theory was modified, and here Kepler told that all planets moved in elliptical orbits. So not the circular orbit, but orbits are elliptical. And what is this ellipse? So this is the ellipse. That's how you can draw ellipse. You have a string at its ends. So this is a string, and its two ends are fixed at F1 and F2. So these are the two focal points, you can say. And in the plural, focus, the plural is foci. Okay, foci means more appropriate pronunciation. Foci. Okay, so pronunciation of foci is foci. So this string, and you can just move this pencil around, you will get a ellipse. Okay, so now an ellipse traced out by the planet. So this planet is also moving around the sun, and sun is at one of the foci. So all the planets in the elliptical orbits with the sun situated at one of the foci. So we have two foci. So students, forget this is another foci. When you are drawing this diagram, you need not to draw this. Okay, so just only draw this. This is just telling you that sun can be here or here, but this you need not to draw when you are drawing pictures. Okay, drawing the figures. Even in your notebooks, no need to draw this. This will create confusion. Okay. So the closest point to the sun is, where the closest point sun is? P. We call this P perihelion. Okay. So this point P is perihelion, and we have point A over here. This point is which is farthest from the sun. See, this distance is, if you see, which distance is the nearest? This is the nearest, SP, this distance, and this SA is the farthest. So here this A is the farthest distance, so we have found 2 points, right? Perihelion and aphelion. Now join these 2 points, farthest, of course. So these points we have joined, we get the axis that we get is semi-major axis, and that's equals to 2a. Half of this is semi-major axis. Half kar diya, semi. So this is semi-major axis, that is a. Okay, and this is from the midpoint of major axis, draw a perpendicular. So this B point and C point, cutting it on the ellipse, and this BC is your minor axis. So this is minor axis, and this was your PA was your major axis, and BC is your minor axis. Okay, so the semi-major axis is half the distance of AP, and P is called the perihelion, A is called the aphelion. So Sun situated at one of the foci of ellipse. This law was a deviation from the Copernicus model, which allowed only circular orbits. The ellipse, of which the center is a special case, is a closed curve which can be drawn as this process. So this we have already discussed. Okay, now let us move to law of areas. The line, so this is the law of orbit from here to here only. Okay, so underline this in your notebook. So these are the key points. So this is the point that you need to write for the law of orbits. All planets move in elliptical orbits with the sun situated at one of the foci of the ellipse, and then you can draw this diagram, and whatever is written over here is you need to know. Okay, this thing is not required. This is just to tell you that how to do this. So this law of orbit, what is written under this figure and up to this point. So these are the key points. Okay, from here, this figure, what is written below this figure, and up to this point. This is what you need to write in your notes. Nothing else you need to write. Okay, so students, you can some of the things you can keep on underlining, and if you are getting time simultaneously, you can write it in your notebook also. It's good to write it simultaneously. Okay, next is law of areas. So now you have this ellipse. Okay, and sun is over here. So here you have the sun at one of the foci. Okay, now we have the earth. Earth is over here, suppose. Now we have a line which joins the earth and the sun. So this is the line joining. So the written over here, law of areas, the line that joins any planet to the sun. So this is the line joining any planet to the sun. Now this line, so now the earth is rotating, suppose in this direction, or any planet. So it will reach here, earth, traveling this much distance, and now this line will reach here. Okay, so we say that this line sweeps. So this area, this line has swept this area. Okay, so this is that area delta A, small area in time, small time, delta T. So now when the earth will reach here, suppose, earth reaches here, so again this line joining the earth and the sun, and then the earth reaches here, and again this line sweeps this much of the area. So this area is also the same as this one, and time taken is also the same as this one. Okay, so this is the law. The line that joins any planet to the sun sweeps equal areas in equal interval of time. So if this is the, suppose, area swept in, this is the area A, swept in, suppose, 10 days. So same area here, A square units in 10 days. So it means Earth has traveled this much of distance in 10 days, and here Earth has traveled more distance. So what does this mean? Area is same, because area is equals to half into base into height. So here, if you see the distance, only this much distance covered by the Earth. But here, on this side, you can see that in the same 10 days, Earth has traveled this much of distance. So it means the speed of the Earth was more here, and the speed of Earth was less here. So here, lesser speed of Earth, and here the speed is more. So when the planet is away from the sun, its speed is lesser. Okay, and here speed of Earth is more when it is near the sun. So near the sun, speed increases, speed of planet increases. Okay, so that is why this is this. That is why this law. So you have to in your notebooks you have to write this much, this one. Okay, that the line that joins any planet to the sun sweeps equal area in equal interval of time. And then what is the reason? Reason is here. Planets appear to move slower when they are farther from the sun than when they are nearer. So this is the reason for this law of areas. Okay, now law of periods. So we have this ellipse, and we have sun over here, and here we have our planet. And it's the sun at one of the foci. Now, of course, there will be more planets. This is another planet. This suppose Earth. This suppose Jupiter. So Earth has some time when it is revolving. What time period of one revolution? Jupiter will also have a time. We write it as TJ, TE, time period of one revolution. Time period of one revolution for Earth is TE. For Jupiter it is TJ. For Earth it is TE. So the square of the time period of the revolution. So square of the time period of the revolution is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. So this is your major axis. Half of it is your semi-major axis. So this is a semi-major axis for AE. And now if you connect the Jupiter also, you will get this is the semi-major axis AJ for the Jupiter, right? Total is 2A. This 2A semi-major axis. So half of semi-major axis is A, right? So this is AE and this is AJ. So TE is directly proportional to AE cube. And for Jupiter, time period of one revolution, square of it is proportional to A, length of this semi-major axis, and cube of it. This is your law of period. So this is what you need to write. The square of the time period of the revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. Okay? And we have table 8.1, you can see in your books. So of course, if I will be writing this for Earth, what do I get from here? TE square is directly proportional to, there will be proportionality constant. Okay. this proportionality sign will change into equal if I write here the constant of proportionality and this AE cube. Now similarly, what about this equation, this proportionality? Tj square is equals to K into AJ cube. So student, this K is same, it is same for both, okay? In case of Earth and in case of Jupiter, this K is same. So what do you get the value of K? So K is equals to TE cube divided this T square, sorry, so just be careful, it's the square of the time period and cube of the half of semi-major axis, okay? And from here K is equals to T J square upon AJ cube, okay? So this is so you can see that it means that these two values are same, T square upon this. So this is what is calculated in table which is there on page 185, table 8.1. So this constant is calculated, and here the units they have taken is years and meter cube. So years for time, the unit is year, and for distance they have taken the units meter. So these are the units that they have taken, and they found the value of K is equals to, so K is for Mercury it's 2.95, and it's for Venus it's 3, for Earth it's 2.86, for Mars it's 2.98, so Jupiter is 3.01, so and then for Saturn 2.98, for Uranus 2.98, Neptune 2.90, Pluto 2.90. So you can add all of them and divide by 9, you will get the average value. So it is somewhere near around 2.98, okay? So K is approximately equals to 2.98. I hope you have understood this, students. Yes?
Yes, sir.
So this is the quotient they have written here as value of K we have just calculated, and that's what that I was discussing with you, okay? So how is this law means the sort of so here the Kepler laws ends over here, okay? So this is this. Now we have the proof that was not given by Kepler, but it was proved later, the law of areas. So this is here the now starts the law of proof. So proof of law of areas, okay? So we have studied 3 laws. So what are the 3 laws? First is that Sun is at one of the foci, that is law of orbits. So Kepler's laws, first was of orbit, law of orbits, which is elliptical orbit. Orbits are elliptical and Sun at focus of the ellipse, right? Second law, that's law of areas. What is this law of area? The line joining the Sun and the planet, the line sweeps equal area in equal time interval. It means we have studied that the planet, when it is near the Sun, it is faster, and when it is away from Sun, planet away from sun is slower. Okay, now the third that we studied is the law of periods. And law of periods states that the time period of the revolution is proportional to the semi-major axis, cube of semi-major axis, cube of it. That is, and we have concluded that t square semi-major axis is your, so major axis is A, semi-major axis, so major axis is 2A, semi-major axis will be A, and here t square by A cube is equals to constant, and we have even found this value of constant in year per meter cube. So now let us find the proof of this law of areas. Okay, so this is over here. So this law of areas can be understood as the consequence of conservation of angular momentum. So what is the concept we are going to use here? Law of conservation of angular momentum, which is valid for any central law. So what's this central law? Central force. Sorry, not law of central force. So central force is such that the force on the planet is along the vector joining the sun and the planet. So this is your elliptical path, and your sun was over here. Okay, that's your sun, and you have the planet over here. So planet is revolving around the sun. So what is the central force? Is the force such that the force on the planet is, so where will be the force on the planet? So force will be, this planet will be attracted, so that's the direction of force. So this planet will be attracted towards the sun due to gravitational pull. So this force is gravitational force. We write it Fg. Okay, so this is a gravitational force. So this force is along the vector joining the sun and the planet. So this is the line joining the sun and the planet, and this is the gravitational force. So this force is along the line joining the planet and the sun. Okay. So these forces are known as central forces. So this is central force, where the force is acting, central force acts on the line joining the two bodies. Okay, so these are the two bodies, and if there is any force acting on them, so suppose here it was gravitational force, suppose you have two charges, plus and plus, so they are repelling each other, or there is a positive and negative charge, they are attracting each other. Okay, so here they are repelling each other. So but the force acts on the line joining the two bodies. So here also, so this electric force is also your central force. Okay, so we have these forces as central forces. So, and for central forces we have the law of conservation of angular momentum. So what is law of conservation of angular momentum? We know linear momentum, P is equals to, that is Newton's second law we have studied. Force is equals to, Newton's second law is force is the force that you apply depends on the rate of change of momentum. So force is Newton's second law, force is equals to rate of change of momentum, and here you put the value of mv, and m remains here, and dv by dt is acceleration. So you get this formula, that is Newton's second law. Now here we don't have linear motion, we have rotational motion, right? So this is the rotational motion of the planet. So here for rotational motion we have moment of force, that is torque. Okay, so in rotational motion we have torque, and torque, torque is, what is torque? Torque is equals to R cross F. So this is torque, and instead of P we have angular momentum. So this was linear momentum, so this is angular momentum divided by dt. So here this angular momentum, same formula, so R into, so it's a linear counterpart, that is a momentum. So this is linear momentum, this is angular momentum, this is force, this is moment of force, and I call it torque. So now if there is so this is external, internal forces cancels out each other, so we talk only about external. Now if this is equals to 0, so what does this mean? It means if the external torque is 0, so it means this L is some fixed quantity, it's some constant, because derivative of constant is only 0. So it means L is a constant. So it means L is conserved. So that's the law of conservation of angular momentum. So L is not changing, L is a constant. So we can use this law to prove the law of areas. So that is the case when we have a central force. Okay, so we have this on the next page, we have this discussion also about the central force. See, this is the central force. The central force. So we know that time rate of change of angular momentum of a single particle about the origin is this. So this I have just written that if F is equals to dp by dt, then it's so this is for the linear motion, and for the rotational motion we have tau is equals to dl by dt, right? So that's and what is tau? So tau is equals to, where tau is equals to r cross f. So this is what is written over here, r cross f, this tau. So r cross f is equals to dl by dt. Okay, so this torque, how can this torque be 0? How can this torque be 0? Torque is equal to r cross f. So what is the magnitude of this torque? Magnitude of this torque is magnitude of r into magnitude of f and into sine theta. Sine theta is the angle between them. Okay, so look at the case here, which is of sun and the planet. So you have sun over here and you have the planet over here. Okay, now what is this r? R is the position vector. So where is the position vector? So this is the sun. So this so we assume that sun is at origin. Okay, so the position vector, this is the position vector, r vector. Okay, directed towards the planet. Now where is the force? So see what we are talking about, the position. Whose position we are talking about? Position of the object on which force is acting. Yes, yes. Torque is acting on the planet. Who is revolving, students? Who is revolving? Tell me. Yes, who is revolving?
Planet.
Who is moving? Sun is moving or planet is moving?
Planet.
Planet is moving, right? So planet is moving. So whose position we are going to take? Planet's position. It's the planet's position, right? And which force on the planet acting on the planet? Is this okay? So torque is acting on the planet. So we will take the position vector this of planet, and this force is also acting on the planet. Okay, so this is the direction of the position vector of the planet. Now what about the force on the planet? In which direction this force is acting? This sun is pulling this planet towards itself. So along this line, yes, that's the meaning of central force. So force is acting on this line, which is the same line as the position vector. So the line is same. So whenever this line is same, so this is the force. This is the direction of force acting in this direction, right? So whenever we have R and F along the same line, so it can be possible that R is in this direction and F also is in this direction. Okay, like we take two charges, negative charge and positive charge. So this negative will be attracted toward this side and this positive will also be. So the position vector and force, they will be in same direction in case of opposite charges. So there the angle between R and F will be 0. Okay, but what is the angle here between R and F? R is in this direction, which is telling you the direction of the planet, and the planet is being pulled by the sun in this direction. So what is the angle here, students? What is theta here between R and F?
180 degree. 180 degree.
So here theta is equals to 180 degree. So that is why in cases of the central forces, so we are discussing here central force, which is acting along the line joining which is acting along the position vector, or which is acting along the line joining the two objects. So here theta can be 0 in case of opposite charges, and here in case of gravitational. And if you have same charges, then again theta will be 180 degree. Okay, so students, actually here when the charges are opposite, here you can say theta is 180 degree, because here we have attraction force and here we have repulsion. So here we can say that you will find that theta is equals to 0. Okay, so in case of electric force, theta can be 180, theta can be 0. So if there is attraction like here, theta is 180 degree. Okay, so just correct it. So I hope you have understood the meaning of central force. And in central force, theta is either so in central force, theta is either 0 degree or 180 degree. So what is the value of sine 0? That's 0. What is the value of sine 180? Yes, what is the value of
0.
180? That is also 0. So in case of central forces, tau will be 0, because sine 0 or sine 180, tau will be 0. Yes. So when tau will be 0, so here tau is equals to 0. So means this r cross f, we have calculated this r cross f, the magnitude of it is 0 if in case of central force. So r cross f is 0 because theta is either 0 degree or 180 degree. So here in case of gravitation it is 180, and so that's that dl by dt. So this means that rate of change of moment, rate of change of angular momentum is 0. It means L is conserved, constant. L is not changing. L is not changing. So what does this mean? This means that this is your elliptical path and your sun is over here and the planet is over here. This is so which is the farthest point away from the sun? That's aphelion. So we have aphelion over here, and then this planet moves round and it reaches here. So this is perihelion. Okay, so the momentum, this angular momentum at A is equal to angular momentum at this position. So at all the position, angular momentum is not changing. Angular momentum is same at all the positions. So angular momentum at aphelion. Angular momentum of whose angular momentum we are talking about? Who is moving? Angular momentum of a planet. Of course, the object which is moving. So the which is in rotational motion. So angular momentum of the planet is constant. Angular momentum of the planet is not changing. So it means angular momentum at aphelion, or suppose at this point we took as B, and this point we took as C. So angular momentum at A is equals to angular momentum at B is equals to angular momentum at P is equals to angular momentum at C. So this is what does this mean? Okay. So if you want to read the angular momentum of the particle is conserved if the torque, which is r cross f, due to the force on it vanishes. So whenever torque vanishes means torque equals to 0. So there are three cases in which torque is 0. So because torque, the magnitude of torque is product of these three values. So either r is equal to 0, or f is equal to 0, or sine theta equals to 0. So if any of these three cases, you will get the torque vanishes and torque equals to 0. So this happens either when f is 0 or f is acting along the r. So f is acting along r means theta is equals to 0 degree or theta is equals to 180 degree, and or f is 0. Okay. And some of the time we have studied that even r is also equals to 0. So we are interested in forces which satisfy the later conditions. So this condition we are means when f is along r, and the forces which satisfy this condition, when force is acting along the r, this forces are central forces. So a central force is always directed towards or away from a fixed point, that is along the position vector of the point of the application of the force with respect to the fixed point. Okay. Further, magnitude of central force depends on r. So further, there is one more point, that this force, so what is, we will study the gravitational force, the formula given by, proposed by the Newton. So that was gravitational constant, and m1, the two masses m1 m2 divided by the distance between them. So that's the mass m1, that's the point mass m2. So these are the point masses. Okay, and the distance between them is r. So then the gravitational force, which is attractive force always, is the gm1 m2 by r square. So this f is this inverse square law. This fg is inversely proportional to the square of the distance between them. And similarly, if we have two charges q1 and q2, and the distance between them is r, so here Fe, electrostatic force, is equals to, so we also have a constant over here, just like we have a constant g here. So it's these values are different. This is electrostatic constant, this is gravitational constant, and that's q1 q2 divided by r square. So see in both the cases, this central force, gravitational force or electric force, they are both of them are following inverse square law, means they are inversely proportional to the square of the distance between them. So this is what here it is telling, that central force always directed towards or away. So it can be directed towards or away because here it is always towards, okay, because gravitational force is only attractive. But here, if the charges are positive or negative, same charges, then they will be repelled also. So this is what it is telling, that central force is directed away, towards or away from a fixed point. So that is so we have this figure also. Further, magnitude of a central force depends on r, that we have just discussed. So the distance of point of application of the force from the fixed point is fr. So students, that is another way you can write here, because this gravitational force is only a function of r, because this g is constant, this m1 is constant, and this m2 is also constant. So here also k is constant, q1 is constant, q2 is constant. So here also I can write it in the bracket FER. So it's better if you write F bracket R here. So this depends on this distance, this FG, and here also I write FE and in the bracket R. And even you can write the vector signs also over here. Okay. So students, that's the central force. So in central force, because the either the means there will be only two cases. The force is either the central force either directed away or towards the fixed point. So angle can either be so either R or F will be in same direction. So there the angle will be 0 degree. So here the angle is 0 degree when they are in same direction, and when they are in the opposite direction, so then what's the, see, in attractive cases we have taken the angle 180 degrees. So sorry, I have to make it 0. So in case of attraction, I am taking this R and F in the means opposite direction. Okay, in case of attraction, and in case of repulsion, so what's the position vector of this point? So this is the position vector of this point, and it is also repelled, so force also in this direction. So here R and F are in same direction in case of repulsion, so that's why theta is equals to 0 degree here. So if it is attraction, this charge is attracted, like here it is attracted, so the angle is 180 degree in case of opposite charges, and in case of same charges it will be repelled. So students, that's very important discussion, and you have understood that whenever there is central force, torque will be 0 because sine theta will be 0, and when torque is 0, then that's the point we have that this L is constant. So means L is not changing. So this derivative is constant. It means the L is conserved. Okay, so initial and final is the same. So if this initial, this final, that's the same. Initial, final, at all the points, L is conserved, L is constant. Okay. So in the motion under the central force, the angular momentum is always conserved, and two important results from this. First is the motion of particle under the central force is always confined to the plane. So this plane of the ellipse, so motion will always confine to this plane. So this can be means whatever the plane it is, the motion will be confined. So here also, if it is repelling it, so then also the motion will remain the same, the plane will remain the same. Okay. Second point is the position vector of the particle with respect to the center of the force, that is the fixed point, has a constant areal velocity. And in other words, what does this mean? That the position vector sweeps out equal areas in equal time as the particle moves under the influence or the central force. So particle will be moving, under the influence of central force, and the position vector sweeps out equal area in equal times. So if this is the case here, so this will be the equal area in equal time, and we can prove these results, and we can find the areal velocity dA by dt, that we can find this from here. See, that you can try yourself if you would like to try. But here our work is done. Means we have discussed this concept, and we have got that when in case of central forces L is constant, and when L is constant, so that is what we knew. So central force is such that the force on the planet is along the vector joining the sun and the planet. Let the sun be at the origin. So we are assuming the sun at the origin over here. Okay. So that's the direction of force. And from origin, what is the direction of this planet? So what is the position of this planet? So the position of this planet is that's the line, so both are along the same line. So this is the position vector in this direction, and here you can see the angle between R and F, this theta is so angle between R and F, so this formula we are taking. So this R and F, the angle between them is 180 degrees. So So torque will be 0. And if torque is 0, so then L is a constant. So let the sun be at origin and the position and momentum of the planet be denoted by R and P. Okay. Now, again, let us draw this elliptical path, and we have sun over here. And let the planet be over here. So that's your planet. So at this point, where is the direction of in rotational motion? Where is the direction of this velocity? The direction of this velocity is tangential, of course. That's the direction of velocity, right? That's a tangential. And what is the position vector? So that's the position vector. That's position vector R. Okay. And here in this direction, we know that's the direction of gravitational force. And this gravitational force is providing this rotational motion. So that's also a centripetal force, and that's also the direction of your centripetal acceleration, isn't it? So say that the centripetal acceleration is towards the direction will be towards the center here. So that's V. That is your tangential velocity, or you can say speed. Okay. So that's the speed, means V, and the direction of the motion is tangential at this point. So what is the area swept? So if we draw one more figure, so my sun was over here, so and the planet was over here. So the planet has reached from this point to this point. So this is the area swept in time delta t. So the area swept is also very small, that is delta A. So very small area swept in very small time. So now you can assume this as isn't it, this very small, sort of triangle. And what is the area of triangle? Half into base into height. So this curve, in physics, when we go very, very near to the circle, very, very near to the sphere, this very, very near as you can, so you will see that this curved surface behaves like a flat surface when you take only small portion of the surface area. So this curve and this is the same. So this is your base. Okay, and then when this angle is very small, this vertical angle is very, very small. So because this distance I'm taking very, very small, B is very small, this. So then this height will also be this length, you can take it as this position vector, even you can take it as a height. So half into base into height. And what is this base? Base is the length. So what is the length equals to? Length equals to speed into speed multiply time. Yes, speed is equal to length upon time. And what is length equals to? Length is equals to speed multiply time. So that's what this length is. So this length is, this B is speed multiply time. So what will be the area swept over here? So this area, I can write delta A is equals to half into base into height. So half into what is base? Base is this length covered, and how much this length covered? That is speed into time. So what is the speed? Speed is V. This V is your speed, and if I'm taking the direction also, so here I'm taking the area as area vector. So this I'm taking the direction also. So this is, but the magnitude is speed into time. Okay. So students, we can take the area as a scalar quantity and as vector quantity also. So area can be scalar, area can be vector. So what is the direction of this area vector? So direction of area vector is perpendicular to the area vector. So that's perpendicular to it. So it can be in upward direction from here if this is coming out of the plane or going into the plane. So it can have two directions. So the area, and So we take the direction of area vector as per our need. So here this is your base, speed into time, the magnitude, and what is your height? Height is same your position vector. Okay, so this position vector. So if you have two vector students and you are getting the result as vector, so it means which product is it dot product or is it cross product? The product of two vectors is a vector. So is it dot product or cross product?
Cross.
Cross product. So that's the cross product. And now you can bring this A over here, delta A. So equal area and equal amount of time means A upon T is constant. This is what the law of area means, that A upon T is equals to constant, right? Yes. So this is what we are going to prove. So delta A upon delta T is equals to, now this is half into R into, what is your P? P is equals to mv. We have written over here also, we have used it here. So P is equals to mv, and what's V equals to? V equals to P by M, right? So V is equals to P divided by M. So V is equals to P divided by M, right? So this delta T goes this side. So this is what do we get? That delta A by delta T is equals to this R cross P divided by M. And what is this R cross P? R cross P is your angular momentum, right? So this is half of angular momentum divided by M. So, and this is constant, half is constant, L is constant, M is constant, right? In case of central force, so our whole idea that we discussed it, we are using it over here. So this L is constant, right? So that we are using here. So M is constant, so it means this whole is a constant. So it means the area swept in time, same time anywhere, will be the constant quantity. Okay, so that's what we have done here, where V is the velocity, L is the angular momentum, that is R cross P for a central force that is directed along R. L is a constant, and then so L is constant as the planet goes round the sun. So hence delta A by delta T is constant, right? And this is the law of areas, that equal area swept in equal time. So whenever same area, same time you are taking, anywhere from here to here, same area, here to here, same area at the same time, here to here, same area at the same time, here to here, so everywhere it will be the same. So gravitation is a central force. Gravitational force is a central force, and hence the law of area. So hence the law of areas is due to, because L is conserved, and L is conserved because theta between R and F is 180 degree, and sine 180 is 0. So it means torque is 0 and L is conserved. So that's the concept. Now very simple example, 8.1. So you have a you have speed of planet So students, we have discussed this case also. So this is what this example is. This is the points here. The point which is away. See how to remember it. Aphelion, perihelion. This is your sun. Let me tell you a simple way to remember it. A for away, so A for aphelion. Away from sun, aphelion. Okay? This is okay, students? So start from A always. A means aphelion, and A is away from sun. Okay? So away from sun, aphelion. And what is this point which is near to the sun? That is perihelion. Okay? So now so it is, the velocities are given. Here the velocity is VA at aphelion, velocity here at VP, and the distance from the sun is RP and RA. So this RA and this is RP. So we have to rate RP and VP. Okay, and we have just studied that this line we have written that momentum at all the points will be same. So momentum at A will be equal to momentum at P. So what is momentum at A? This angular momentum is equals to R cross P. So what is the magnitude of L? Magnitude of L is here in this formula you can see L is R cross P. So what is the magnitude? R, magnitude of position vector, into magnitude of P. What is P? P is equals to M into V. So that's the magnitude. So it means this mass into the distance from the sun and the velocity at perihelion is equals to mass of the planet. So mass of the planet is same at both the planet, it will be cancelled out. So you will get Vp upon Va is equals to Ra upon Rp. Now you know that this Ra, this distance, this Ra distance is more than this here, this Rp, right? So Ra is greater than Rp. So Ra is greater than Rp. So it means Ra is greater than Rp. So this number is greater than 1. Ra is greater, numerator is greater. So it means this number will always also be greater than 1. It means Vp will also be greater than Va. So it means Vp. So here speed is more, Vp, and here speed is less. So it depends on the speed depends on the distance. Okay. So if Ra is more, then Va is less. Okay. So if Ra is more, then Va is less than Vp. Is this clear? So distance is, if Rp is more, then Vp is less. Students, same thing like this, greater than this same kind of questions we do in physics at many places. These variables will change, like we'll study transformers. Okay, and there will be studying same way like transformers, you know, that they change DC to AC. Okay, direct current to AC current, and same thing we'll study over there also. Same kind of, the variables will change, but the same discussion. If this Ra is greater than Rp, then Va will definitely be smaller. So the numerators will be greater and denominators will be smaller. So students, whatever you are studying, gaining knowledge, don't look at means that just to clear class 11. No, these are the basics that you will be requiring to study physics, and the knowledge that you gain, that will be for the lifetime. So you are studying for your own knowledge. Okay, so hence the area bounded by the ellipse due to this radius vector SB. So and SC is so here it is asking you, next part of this question is that the B part, will the planet take equal time in traverse this BAC and CPB? You have the figure, so that's point B over here. Yes, and here I have point C. So B is over here and C is over here. So he is asking you that will the planet take equal time in traverse this distance? So here it is away from the sun and here it is near to the sun. So will the time be same, students? definitely here it is
No,
slower
sir.
and here it is faster, so time cannot be same. So Kepler's second law, equal areas are swept in equal time. So what is the area here? See, what is the area swept? See, join this line from the center of the sun. Don't get it confused, this area. No, not this area. Join the sun with the planet here. Okay? And this is the area. It is sweeping. This line is sweeping until the planet reach here. So see, this area, it is sweeping over here. Okay, so equal area in equal interval of time. So time taken from here, you know, but so this area is this area. So but here we are talking about, will this distance BAC, so definitely the planet will take longer time to traverse BAC. So this is BAC, because this area, you can see this is your half area, na? This is your half area, so it is sweeping more than half of the area of the planet. Do you understand? See here, it is sweeping this much of area, right? And what is the half of the area? This is your this half is here, right? And you are sweeping this much more. So how can time be same? So if you draw minor axis, so then this half and this half, so time will be same, area will be same, minor axis. But I am not taking this minor axis over here. I am taking this FAC, this point, sorry, this B and this sun at point S. So I am taking BSC. So this area is definitely more. So that is why the speed here will be slower and here it will be faster. Okay, students. So students, again, whenever there will be next revision class, be ready to attend that class. Thank you so much. That's all.